let's start with some properties of ionic compounds here. Do y'all remember the properties of ionic compounds that we wrote on our lab sheets a couple weeks ago? No?
Maybe.
That's one of them, yeah. High melting point.
Conductive.
That's another one.
Wasn't this on a test? Harsh.
Nope. This was not on the test. On the test, I asked you about covalent properties. But for ionic, we got, high melting point, conductive, so they conduct electricity when you dissolve them in water. And like Alina just said, we also know that they dissociate in water. That was covalent. Ionic compounds are more brittle. And they're often crystalline, which means like they're crystal-like. You think about like table salt. That's an ionic compound. Any other ionic properties that you guys remember? I think that might be all of them. Cool. Let's move on to some examples of ionic compounds. One of them I just said, it's going to be salt. And salt was one of the compounds that we used in our lab. The other ionic compound in our lab was, calcium chloride. Calcium chloride. And let's do another example. Say magnesium sulfide. How about that one? That's another example of an ionic compound. Just like when we took our covalent notes, I also want you to have the chemical formulas of these. Salt is otherwise known as sodium chloride, NaCl. Calcium chloride is CaCl2. There's 2 chlorine atoms, or 2 chlorine ions. Then magnesium sulfide, that's MgS. If you got questions on how you know that that's the formula, we'll get there. Thank you. But let's do definition. How do we know that we're looking at an ionic compound? Well, do you guys remember what you wrote down for definition of covalent compound? You guys remember? You can flip back a couple pages in your notes. Brianne, you got it? Yes, that was one of the things that you wrote down. Covalent compounds, those atoms are sharing an electron pair. Ionic is a little bit different. Ionic compounds are formed from not the sharing of electrons, but the transferring of electrons. So you can say formed from transfer of electrons. Another important thing to know about ionic compounds is that they are not actually made of atoms at all. Ionic compounds are made of ions. And if you remember from our atomic structure notes, ions are atoms with a charge. Charged atoms. By the way, review again, we can get an ion, or we can have a charged atom if we have unequal numbers of protons and electrons. So if I have like 5 protons but 6 electrons, that's an ion. It's got a charge. What was the other thing that you wrote down for covalent definition? Good, yeah. So covalent is between 2 nonmetal atoms. An ionic compound is made from 1 metal and 1 nonmetal. In general. We have to have a metal and a nonmetal in an ionic compound. So for instance, let's look at our examples. We have sodium and chlorine as our 2 elements in sodium chloride. Sodium is a metal because it's in the alkali metals, right, at the far left of the periodic table. And chlorine is a nonmetal. That's a halogen. 1 metal and 1 nonmetal. So that is that. Okay, so at the beginning of the notes, I said that I wanted you to make your paper look like mine. Braden, you need your notebook out. We're taking notes today. But I do not need you to write what I'm about to write. I'll let you know when I want you to start copying me again. I just need you to pay attention on this. So I'm going to draw a lithium atom. A lithium atom has how many protons in its nucleus?
8.
No. No.
2.
No.
3.
It's the atomic number. What's the atomic number of lithium? It's 3. Lithium is 3. Yeah, it's in the upper left of the box. Great job. So if a lithium atom has 3 protons in its nucleus, it also has 3 electrons orbiting around that nucleus, right? I'm going to draw in those electrons. In the innermost ring, I can fit 2 electrons, but then I'm out of space, so I need to add another ring. Yes. Now that right there, that is a valence electron, and I only have 1 of them, right? And for all of the elements in that first column of the periodic table on the far left, they all have 1 valence electron, right? This is what helped us figure out Lewis structures, yeah? A couple weeks ago. But now, I want to see what happens if I take this electron and pull it off of that atom, okay? Now, how many protons do I have in this ion? No, I still have 3, because I didn't take away any protons, right? I just took away an electron. I still have 3 protons. How many electrons do I have?
2.
I have 2. Electrons, of course, have a negative charge, so there's, like, overall, the electrons in total have a -2 charge. The 3 protons means that the nucleus has a positive 3 charge, 3 plus. Now, the charge in the nucleus does not cancel out with the charge in the electrons. Overall, are we going to have a negative charge on this ion or a positive charge on this ion? Positive, because we don't have enough electrons to cancel out all that positive charge in the nucleus. So this lithium ion has a charge of +1. And by the way, when I take away this electron, that goes away. And that is ionization. That's ionization energy. The amount of energy required to do that, to pull away that electron, that's ionization energy back from periodic trends. Can you flip to an open page in your notebook, Braden? And can you hand Harry your phone so we can put it on my desk? Okay, so that's lithium. I want to jump down and to the right. I want to do magnesium now. Let's do magnesium. Magnesium has 12 protons in its nucleus, which means that if I'm dealing with an atom of magnesium, I need 12 electrons also. Cool?
Are we writing it?
Nope, still not writing this. I'll let you know when I want you to write again. So again, with magnesium, I can only fit 2 electrons in the innermost ring, and I need to add another one. Not 10, right? Because this second ring can fit 8. Yeah? That one can fit 8. If this is new information to you, that's okay. Okay. So I need to add a third ring. The third ring can also fit 8. The rest of them can fit 8. Okay. So, but I don't need 8 because I've already got how many? 10? So I need 2 more. Just like that. Now, guys, I'm going to take this magnesium atom and I'm going to turn it into an ion. The way that I do that is not, this time, not by removing 1, but by removing 2 electrons. I'm going to pull those off. And when I do that, that outermost ring disappears because there's no more electrons in there. Michael, pay attention, please. The reason that magnesium wanted to lose 2 electrons is because once it loses 2, check it out. Now it has an octet as its outermost valence shell, right? Now it's got 1, 2, 3, 4, 5, 6, 7, 8. And octets are great. Octets are very stable. So the magnesium is not super happy just losing 1 electron. It's going to give 2 electrons away, okay? Because it wants to get to that octet. But now, in order to get to that octet, it had to lose 2 electrons. How many electrons does it have left?
10.
It has 10 electrons left. How many protons does it have left? Still 12, because we didn't lose any, right? We didn't get rid of any. That's a charge of plus 12 in the nucleus and a charge of negative 10 going around that nucleus. So overall, is it going to be a positive ion or a negative ion?
Positive.
Positive again. But this time, we have a charge of not plus 1, but plus 2. So this is why different ions have different charges, because they've lost different numbers of electrons. Maddie, can you stop? I'm recording this, by the way, so I don't want it picking up your voice. Yeah, thanks. Okay, so lithium ions have a positive 1 charge. Magnesium ions have a positive 2 charge. Now, I'm not going to ask you to draw out the structure of the nucleus with all the electrons around it and count them up. That would be a lot of work, and that would take a lot of time. Okay, so I don't need you to do that. I did want to show you so you can see why different ions have different charges. What I need you to write down is this. I need you to start a new section and call it charges of monoatomic ions. Charges of monoatomic ions. Because if we know that lithium is always going to have a plus 1 charge and magnesium is always going to have a plus 2 charge, I bet you there's a pattern in there, right? Because the periodic table is arranged in such a way that there are a bunch of patterns. So let's discover that pattern. It's a pretty simple one. Let's go down the first column. Hydrogen, lithium, sodium, potassium, all the way down. I'm not going to write the rest of them. But all of these, when they turn into ions, when they lose electrons, they're all going to give up their 1 valence electron, which means that they're all going to end up with a charge of plus 1. If we go 1 over to beryllium and magnesium and calcium, all of these are going to have a plus 2 charge. They're all going to give up 2 electrons. They're going to give up their 2 valence electrons. We're going to skip over the transition metals. We'll get to those maybe on Thursday or Friday. But I'm going to skip over to boron, aluminum, and germanium, Ge. All of these have a charge of +3. By the way, you are writing this. I do want you to write this because you're going to need it in a second. Yeah, all the way down. I'm just writing the ones that you're going to see most often. Yeah, because I don't want you to write a million elements. Carbon and silicon we're going to skip because those don't show up very often in ionic compounds. And when they do, their charges are weird. So we're going to skip those for now. And we're going to go to nitrogen, phosphorus, and what is it?
Arsenic.
Arsenic, thanks. Any guesses on the charges on these ions? You would think, right? Like +5?
Wait, no. If it's plus minus, it's plus.
Actually, it's -3.
Yes. And then it goes
Why?
negative 2.
Yes.
Because why take 4 when it can just take 3?
Going 1 over again, we got oxygen, sulfur, and selenium. Maybe you can see the pattern now. These are -2.
So on.
Still write it, though. We got fluorine, chlorine, bromine all the way down, -1. The noble gases to the far right, they're not going to be involved in ionic compounds because they're not involved in any compounds at all. It's chlorine. What's up, Harry?
So you know how the transition metals when we were like drawing the Lewis compounds? Is that what's called? Lewis compounds. Anyways, how like we had to like count the rows so we knew how many dots we needed,
Mm-hmm.
but we didn't like use the transition metals.
Right.
How do you draw a Lewis compound for that?
Okay, good question. In ionic compounds, that's the only places that we would have transition metals. And for ionic compounds, there are no Lewis structures that we're going to be drawing. We will look at some ionic compounds that use transition metals, but they don't have nice and easy rules that we can learn. Like it doesn't go +1, +2, +3 across the transition metals. It does something kind of weird. Yeah, each one is a little bit different. And so we're not going to deal with those until we've got a good grasp on these simple ionic compounds. Cool? So for today, don't worry about the transition metals. We will get there. Okay. Now, when we go to name our when we go to name our ionic compounds, the names of the compounds are going to look kind of similar to the names for covalent compounds in that it's made up of a first part and a second part. The first part is always going to be the name of the element with the positive charge. The second part is always going to be the name of the element with the negative charge. But it's going to have that "ide" ending again. So for instance, NaCl is sodium chloride. Sodium, that's just the name of the element with the positive charge. Sodium has a +1 charge. So it's just sodium. The second element in that formula is Cl, which is chlorine. And chlorine, when it turns into an ion, has a -1 charge. So that's going to go second. Yeah. But we change it to end with "ide", so it's going to be chloride, sodium chloride. What's up?
Is it ever like 2 positive charges?
No. If it's 2 positive charges, then they won't bond together.
What about 2 negative charges?
They won't bond.
They won't bond to each other either.
Opposites attract.
Do y'all have room under first part and second part? If you have room somewhere, I'd like you to add in a couple of examples. Because occasionally, come on, I will refer to, I'll refer to the first part as the cation, and I'll refer to the second part as the anion. Cation and the anion. There are a million mnemonic devices that you can use to remember which is which. I'll teach you those later. I don't really have time right now.
Yay.
Excuse me?
I was cheering so we don't have to do.
Oh, he said yay. Okay, cool.
He's recording. He's recording.
What's up, Michael?
Who's recording?
Take a mental picture, Michael, because I'm moving on. Hey guys, if you are slow at writing, I'm posting this video and I'm posting the PDF. Okay, so you can re-listen to me explain it, and you can just see the PDF and copy your notes if that's what you want to do. Anion.
Man, I'm right there.
I'm sorry, Michael. You can get it later. Okay, so that's the first part and the second part of the names. Let's do some examples. So new section now. Call it naming ionic compounds. Are those your notes?
Yeah. It was her writing because she couldn't talk.
Okay.
Well, I have the video, so I.
Okay. Okay, naming ionic compounds. Let's do a real easy one. Or sorry, this shouldn't be called naming ionic compounds. Because guys, the more difficult part is going to be, I'm going to give you the name and you're going to write the formula. Okay?
Formulating
Yeah, so let's write
formulating the names of ionic compounds.
well, you're not formulating the name.
Formulating compounds
Let's say-
in the name.
Let's say ionic formulas.
Formulation.
Formulation? That sounds like you're making the compound though.
Okay, cool. I'm ionic formulated.
Let's say ionic formulas. Okay, first example, we're going to do one that's kind of annoying. We're going to do sodium chloride. And this is NaCl, but I'm going to show you how we know that it's NaCl. Maddie, shush. Okay, so the first thing that you're going to do when you open up your test and you see, oh, sodium chloride, what's the formula for this? You're going to ask yourself, okay, what's the charge of a sodium ion? It's +1, and you're going to write that down on your paper. And then you're going to say, great, what's the charge on my chloride ion? Well, I know that's Cl, and I know that has a -1 charge, right? And you totally can look at the periodic table to help you figure that out, or you can just do the practice that I'm asking you to do, and you will naturally memorize these, okay, if you do enough practice. So Na has a +1 charge, Cl has a 1- charge. Those two charges just so happen to cancel each other out perfectly. Yeah? So I'm going to end up with an overall charge of 0 if I just plop these two ions together. And that's perfectly great because I always want an overall charge of 0. So this one's really easy. It's just NaCl. Let's do another example. How about magnesium sulfide? On this one, magnesium is Mg, and it has a charge of +2. Sulfide has a charge of -2. So again, these two charges cancel each other out, which means I only need one of each ion. Super easy peasy. Mgs is my answer here. Now, I heard Nick ask the question earlier, does it always work out perfectly where you just have the charges balance each other out. No, of course not. That'd be too easy, right? Sometimes you get something a little bit funky. Let's try to do calcium bromide. Calcium. What's the charge on a calcium ion? Nope. +2. How about a bromide ion? What's the charge on that one? Back at your notes. You wrote it down.
What'd you say?
-1. Now, this does not balance out,
Yes.
right? I got a +2 and a -1. That doesn't add up to 0. But check it out. What I can do is I can add another bromide. Because now these two negative charges combine to create a -2 charge. And that -2 charge balances out with the +2 charge. So that is how we get CaBr2. Because we need 2 bromides to cancel out the +2 charge from the calcium ion.
Mr. Saldana,
Yes,
you know when you screen record, they can't hear your voice, right?
they can.
You can turn it on. So
That's how I made all the videos that I posted over the
You
weekend.
have to hold down on the screen record button, and you can use it.
You can?
Yeah, you gotta long press on the thingy, and it'll say microphone on, microphone off.
Why does it not have dye in front of bromide?
Oh, great question. Hey guys, listen up. Nick just asked a great question.
Good job, Nick.
So Nick said, why isn't it calcium dibromide? Well, because the only way that we can make an ionic compound with calcium and bromide is to have 2 bromides and 1 calcium. That's the only way. So we can't have like a calcium monobromide. We can't have a calcium tribromide. So if you can't have those, then what's the point of putting in the prefix? Yeah. Remember I said chemists are lazy, right? They're not going to give more detail than you need. Right? So there are no prefixes in ionic compound names, which makes it quite easy to name them, right? It's writing the formulas that takes a little bit of work.
It just seems like it'd be easier if it told you there was 2 negative bromides.
It would actually be easier if you didn't have to write the 2 letters DI every time you want to talk about calcium bromide.
Just held my hand.
You see?
I put my hand right here.
Because like why are there so many other side conversations happening? Quiet down,
Because
please.
they lost your focus. I mean, their focus.
Do we need a little brain break?
Yeah.
All right, take 2 minutes. Please. Let's do some examples now that are not so super easy. Let's try this one. Let's try magnesium nitride. Can you guys try this one on your own, actually? Try this one on your own. Brayden, give me your phone. Brayden, give me your phone.
Wait, Mr. Saldana.
What's up, Michael?
What else you gonna play?
N. N is nitrogen. Nitride is nitrogen. Yeah, see, this one's a little bit trickier, huh?
Nitrogen's 2.
Mg plus 2 and minus 2. Right?
Nitrogen has a -3 charge. All right, y'all. Come back to me. Quiet down, please. Y'all are talky today.
I think I know how to do this.
Yeah? Michael, what'd you get?
I
Michael, that's perfect. Yeah, exactly. So you gotta add another wait a minute, what'd you say? No, yeah, you got it. You said you added 2 more magnesiums,
And one more nitride.
right? And that's positive 6. And you add 1 more nitride. That gets negative 6. Right? Basically, what Michael did was he noticed that if I have 2 nitride ions, that's a charge of negative 6 because I got the negative 3 and the negative 3. And then I need 3 magnesium ions to get to the positive 6. And that's how I can get my positive 6 and negative 6 to cancel out, add up to 0 charge overall. So I need 3 magnesiums total, Mg3, 2 magnesiums total, N2. Just like that. Mg3N2. That is the formula for magnesium nitride. Now, can y'all use Michael's fantastic problem-solving skills to try another one? I want y'all to try aluminum oxide. Try aluminum oxide for me. Ready, go.
Here's a little space right here.
Yeah, I know it's heavy notes today.
Where's aluminum? It's 3. Is it Al? Oxygen is minus 2. You gotta do the same thing. It's Al2 O3.
Y'all get Al2O3?
Yes.
Al2O3.
That sounds like a fun
All right, y'all. So, sorry, I'm trying to move kind of quickly because we got more to get through today. But I want to show you a really, really easy way to get the answer to this. Check it out. Look. So once you write out your ions, Al3 plus and O2 minus, or negative 2, you can do this.
Switch them.
You just switch them. The charges become the subscripts of the other ion. Yeah? This is called the crisscross method of writing ionic compound formulas. And it makes everything like stupid easy. So, yeah, that's that. Oh no! It's back. That happened in first hour too. I don't know why.
Are we done?
No. We're probably gonna work to the bell, especially since I gave you that brain break.
We should do fill in the blank.
I feel like that was a neat.
No.
Yes.
Should we do another one?
No.
Or do you want to move on to the more complicated version of this?
We can do the more complicated version tomorrow.
You want to do notes 2 days in a row?
Yeah.
Okay, well, in that case, I'll give you guys some, no, we're going to do practice till the bell. Sorry, guys.
Can I have my phone back at least?
No, we're going to do practice till the bell. Shush. I don't think this is very unreasonable, guys. We're in chemistry class. We're going to do chemistry, okay?
Till the bell, though.
Yeah, to the bell. We missed 2 days of instruction.
Your mood has gone a lot up since you've been in this class.
Yeah, we were here. We showed up every day.
Okay, friends, you're going to follow along with these, right? You're going to try sodium bromide. You're going to try magnesium chloride. You're going to try potassium sulfide.
Donnie, which one's sodium?
Look it up. Oh wait.
I don't have my phone.
How do you know?
Let's do aluminum fluoride. We can honestly just do these like for the rest of the time. We can do these till the cows come home. And we're gonna do them forever then. How about rubidium? Let's do rubidium selenide. Let's do that one. That should take you the rest of the time. Maybe not. If you're done, you're done. But you got to do those. I'll be walking around and bugging you.
This drains your battery.
Yeah. I'm screencasting and recording, so.
We're at like 95.
I can't see that far.
Here.
What are the numbers?
You wrote them down in your notes.
I'm just gonna fall over if you don't put